Hey guys, welcome back to the academic powerhouse with your mathematical meathead himself, the realest guy in the room. Bada bing, bada boom. How you doing? How you doing? Let's talk about those practice problems. Here we are with the solutions video, and here I'm gonna remember we just had four problems, guys. Four related to stem and leaf, histogram, dot plot, and frequency table. Now, the idea was to be able to take from our shapes and convert them into our list of numbers, our measures of center, and our measures of spread. And I have worked all these out and I will go through them with you guys. And I hope you did great. I hope you did great. If you didn't do great, here you go. Here's how you solve it. So let's dive right in. Problem number one. We were given we were given a stem and leaf plot, boiling points, different temperatures. Now, there was a special note. If you didn't see the last video, the special note, the key on the assignment itself had shown to consider, for example, let me write this out for us. Let me write this out for us here, what the key had shown and what I had told you to do instead, just as a little bit of a reminder. The key had said something to the effect of consider that if you see, for example, 1 and 8, for example, it said show 18, do consider that to be 1800. In our case, for the simplicity of our numbers, just to solidify the concept, I said no, just consider it to be 18. So hopefully you recognized that and didn't create a whole lot more work for yourself than was necessary. Anyways, so so stem and leaves again, they give us a shape all on their own, right? You can see that you can sort of trace the shape around kind of how the numbers fit, and it is in fact a shape. In fact, it's you can kind of think of it as like a dot plot flipped on its side, right? So, if you were to see, I'm just kind of trying to trace what I'm seeing here. That would be the shape. Right, here's your horizontal. Here's your vertical. Whoop, that was bad. Erase that. There we go. Right, that's kind of how your data points would look. Right, that's basically, that is your stem and leaf. It's just flipped on its side. But in any case, guys, in any case, listen, here we are. How did I get these data points? That was the first thing that was needed to be done in order to solve everything. So how did I get these data points? Well, first of all, recognize that from a stem and leaf plot, what you're saying is the stems, right? You can kind of think of this as, um, or even on a, I'll do a tree. How about that? Tree. Branches, stems, whatever you want to call it. Right? But trees have lots of branches. I'm doing my best attempt at drawing a tree here with a lot of branches. And on those branches, you can think of them to be the stems. And on those branches, you have a lot of little leaves happening. That's the name that is the name. So a branch, or the leaves signify, well, actually let me back up a second. The stems, so consider them to be the branches being numbers that fall between 0 and 9, numbers that fall between 10 and 19. So your 10s, your 20s, your 30s, your 40s, your 50s, and so on, or your hundreds and 200s and 300s and so on, or your millions and your 2 millions and 3, 4, 5 millions. Really, what it's saying is, let's say if your data set had the number, which ours in fact does, 18, if that was one of our data points, the stem and leaf, the way it's structured is, once again, it's like you're splitting the number in half. You're just cutting it with a knife, basically, right down the middle. And you're putting the first number, the leading number, if you want to call it that, out to be a stem, of which you'll have many of the same type of stem, right? So the idea is you're consolidating them all, right? So you're cutting this off, you have both of these are one, so you're not going to write one and one and one and one for however many you have. No, you're just going to consolidate it all into one different or one single stem. But in any case, guys, that's essentially the structure of it. That's how I determined the list of data points. Is I recognize that each time each time I see a zero, instead of it's well, yeah. Each time I see a zero, I'm basically combining this and this one, and this and this one, and this and this one, and so forth and so on down the line. Now, with zeros, we don't have to explicitly write the zero in front. That's why you see up here, I've left it as just 1, 1, 1, 1, 1, because there were 4 ones, 3, and so forth and so on. And like this one here, I just took the outside, combined it with this one, combined it with this one, combined it with each one down the line. So 22, 25, 26, which you see here, 29, and so on. So that's how you extrapolate the numbers, the list of numbers. Not too bad on a stem and leaf, guys. Not too bad at all. So, with that said, once we have our list of numbers, we can then do what we are hopefully very comfortable doing now at this point, calculating our measures of center and calculating our measures of spread. So we have to recall what they are. The way I did it was I broke it into each, I just did all my centers first, then I did my spread first. And I recalled that mean is the addition, the sum of all of these data points together, divided by the total number of them. So when I added them all up, 1 plus 1 plus 1 plus 1 plus 3 plus 4, and blah, 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 and all the way down the line, added them all up, I got 203. And then I counted each one, right? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so on and so on. And I counted up to 17. So what this means is you're dividing the number 203 by 17, and you get 11.9. I'll come back to that in a little bit. But that is your mean. That is your average temperature. The median, as you are aware at this point, the very middle number in all the list of numbers, the very one in the middle, meaning that there's an equal number of data points to the right of it and to the left of it. So how's this the middle? Let's see, 1, 2, 3, 4, 5, 6, 7, 8. There's 8 on this side. There's 1, 2, 3, 4, 5, 6, 7, 8 on this side. So there's 8 on each side. That means it's equal. That means I know it's the median, therefore 9. Mode, it's the number that occurs most often in your whole data set. In this case, I see the number 1 as repeating 4 times. No other number repeats 4 times or more, so therefore the mode is 1. Easy enough, guys. Range, take the maximum number, which happens to be 32, subtract the lowest number, which happens to be 31, and get your range. So so 32 minus 1 is 31. Get your range. The range itself is 31, meaning that all of your data points fall within 31 whole numbers of each other. Now, interquartile range, a little bit more calculation heavy. Well, no, actually not calculation heavy, but you do have to recognize what it even signifies. It signifies that, yes, you took your median, and that's great, that's your middle, but interquartile range means you're taking the median, a subsequent median of your upper half, so this is your upper half, and a subsequent median of your lower half. You're cutting those two halves in half itself. And you can see, so Q3 is the upper half, Q1 is the lower half. As you can see in this half here, I said there was 8, right? Well, there's no clear number in the middle, which means you take the average of the 2 that are in the middle. In this case, 1 and 3. 1 plus 3 is 4, divide 2, that is the average. You get 2. That's why Q1 here, I have a 2 here. And when I do the same process to the upper half, I don't have a clear middle, so I take the 2 that are in the middle, average them together. 22 plus 25 divided by 2, you get 23 and a half. That's my Q3. That's why you see it plugged in here. There's my 2, as I said earlier. Subtract them, and the range of the inner quartiles is 21.5. And this comes a lot into play when we're talking about box and whiskers. On this assignment, you don't have it, but you still need to know how to calculate it. So that's why we did that for practice. Now here's the most calculation heavy item that we have had to do on this assignment. It is the mean absolute deviation. In fact, half of this page is dedicated just to doing that calculation. Right? Mean absolute deviation, once again, is the idea that anything that isn't, any data point that is not your mean exactly, right? 11.9. Anything that isn't your mean deviates from it, is different from it. That's what deviation means. It's different from the norm, or the most common. So for example, 22 is not 11.9, 25 is not 11.9, and so forth and so on. In fact, none of these are, which is okay, that makes sense. Now, so that's the idea of deviation, and then the whole idea of mean absolute deviation is find out all of your deviations and then take the average of those deviations so that you can say, let's say if this here, I'm just making something up here. I'm saying if this was our 11.9, I'm saying on average, when I do this, on average, how far is every other data point from that center? That's what it's saying, guys. So, how do we calculate? How do we calculate? Well, what I do is I set up a table first. I set up a table where I look at every data point and I set up um, a little subtraction, right? To determine a deviation in the first place, you have to uh, determine how far away it is from the average, and to do that is through subtraction, right? So, for example, this first data point, well, actually, what I had actually done was I did data point minus average. I did it like that first. Ultimately, it doesn't really matter, but that's how I typically do it. And you can see up here now, what you're seeing here is this weird X with a little line above it. Now, rather than me write 11.9 over and over and over again, for the sake of simplicity, I had chose to assign this to a variable and then repeat the variable, just for the ease of me writing. You could do that, or you could write 11.9 over and over again. It's up to you. That's how I do it, though. Right? So I'm saying that when you see this, it means 11.9. So that way, when you see it over here, it is in fact 11.9. So with that said, I just put all of my data points in vertical order, right, up and down. That's what that means. So as I've done here, my 1s, my 3s, my 4, 8, all these numbers that you see up here are repeated. Okay. So all I do then at that point is just subtract. Subtract my average away from each data point, and I end up with some sort of a result. Now you're asking maybe, what are these bars here? What are these lines on the side? They're not just for making it look pretty. No, no, they have meaning. It is it's the A in MAD, the absolute value. It's essentially a way for us to disregard the negative numbers when we're um, trying to determine what our average deviation would be. So for, like I said here, if this was in fact our 11.9, you know, based on the number line, that values to the right of something are positive, values to the left of something are negative. And if we were to include negatives, it would sort of mess up our idea of how far on average is something away from it. So that's why we do absolute deviation. You don't have to necessarily know all that necessarily if you want. I mean, it's good knowledge for sure, but understand that I know 1 minus 11.9 is in fact negative 9.4. I know that to be true. However, because absolute value, it actually is, I'm working with positive numbers. That's why you don't see any negatives here. Anyways, little extra info. Just know that take the deviations, average those deviations, and that is your mean absolute deviation. So I've done exactly that. I've taken each data point, subtracted off the average or the mean, ended up with a result or a deviation for each data point, and then I averaged them out, just like we've done here. Mean is average. Those words are interchangeable. Sum, add them all up. When you do, I get 140.65 divided by the total number of them. As we said before, it's 17. There's still 17 here. That didn't change. So when you do that division, you get 9.45, which there it is, 9.45. That's it, guys. That's it. That is for each of these problems. That is what is to be done for each of these problems. The steps are the same. The shapes, the distributions given to you are different in their appearance. The data points themselves are different, but the process is the same. And that's what I teach. I teach process. I teach the algorithm of getting to the right answer, and you know, each and every time. So there you go. Let's roll into number 2 here. You can kind of see it play out very similarly, much the same way. Number 2, we had a frequency table. The key, the biggest difference, because it is a different visualization, a different shape, a different distribution give it to us, we have to know how to extract the data points from it. Now, a frequency table is simply saying that there are eight number ones here. So I've listed out 8 number ones. There are 2 number 5s here. I've listed out 2 5s, and so forth. That is a frequency table. It's just a summary uh, of all the different data values without having to write them all out like this. You could just say, here's all the ones I have, here's all the 2s, etc. So recognizing what a frequency table is telling you, recognizing how to interpret this data, will give you your list of data points. And from there, the steps and the calculations are all the same. I found my 3 measures of center. Mean, 2.47, median, 1, mode, 1, spread. I have range, interquartile range, and mean absolute deviations that I had to find. Range was 7. Interquartile range was 3. And then my mean absolute deviation, again, I set up that big table, subtracted off the 2.47, so 1. So for example, 1 minus 2.47 gets me 1.47. I did it for each data point. I ended up with a complete list of values that are in fact the deviations from the mean. And then of those deviations themselves, I took the average of those. So add these all up. 25.33 divide 15 equals 1.69. There you go. That's it. That's number 2, guys. Simple. Simple, simple. Number 3. Again, the key difference is recognizing that how to extract the data points is really the biggest difference between all these. So here's our given distribution here, and you can kind of tell the shape as it is, but I like to draw it out above it anyway. Why not, right? There you go. That's kind of the shape. You can kind of see the data points are, most of them occur toward the center. In other words, not on this extreme ends, not on the extreme ends here. Right? They all seem to, as you get closer to the center, there's more and more of them. But anyways, there you go. This is a dot plot. So what it's saying, each tick mark means increments by 1. So what it's saying is that this one is 11, this one's 12, this one's 13, and so forth and so on. And so for each dot, so for example, on this 11, there's one dot at 11. That means there's one data point of number 11, which I have here. On 12, there's one dot, so there's one data point of 12 here. And on 13, you see 1 dot, 2 dot, 3, 4 dots. That means there's 4 data points of number 13, which I've listed out here. So that's how you extract the data from these dot plots to get your list of numbers, and you just do the same stuff from there. Find your measures of center, find your measures of spread. The mean I got was 14.87, median was 15, mode was 13, range was 8, interquartile range was 4, mean absolute deviation, remember I had to take this, I had to take data point minus the mean. In each case, got a deviation for each original data point, took the average of those deviations, got a 2. Well, it's really more like 2.003 or something like that, but I usually round off to 2 decimal places, and it's kind of silly to put 2.00, so I just left it at 2. So there it is. Your mean absolute deviation is 2. That's it, guys. Last problem here, a histogram, or a bar chart if you want to call it that. So what you are to interpret from this is that you have different data points, right? You have, in this case, they're doing years, but it could be anything really on the horizontal. Oh, erase. Could be, could be anything on the horizontal, but the important thing here is to recognize the vertical. The vertical means the the amount. The amount. So for example, if you interpret this chart correctly, what you are to read here is that in the year 1960, 5 gold medals, or just medals, not gold, but just medals, were awarded. And for example here, 1984, 12 medals were awarded. And so that is how you generate your data points, is you recognize that the vertical is the one that's really going to give you the each different value, the frequency, or in other words, the count, if you want to call it that, right? So so this 2 goes, 2004. There was only 2 medals awarded. 3 happened in the year 2012, and there was 1, 2, 3, 4, 5 years in which 4 medals were awarded. 1, 2, 3, 4, and 5, and so forth. And that's how you sort of extrapolate your data points. That is the key on this one, to figuring it out. So once you have your data points, once again, do your 6 calculations, 3 for center, 3 for spread. Got my average here, 5.29. Got my median, 4.5. This one was a little, no, actually, no, never mind. No, I was thinking of something different. Anyways, yep, median 4.5, mode 4, there's 5 4s, range 10, so forth and so on. For my mean absolute deviation, I took each data point, subtracted off the mean, ended up with a full table list of deviations. Average of those deviations gets me 1.84. Easy day, guys. Easy day. Not too bad. Not too bad. Maybe maybe a little calculation heavy. That's why I only gave you 4. Okay, lots of opportunity. But if you got the process, if you understand the basic steps, the biggest difference, as I said, is extracting the data points from the visualizations you're given. When you're able to extract it, you can then calculate center, calculate spread, and as I've said ad nauseum at this point, when you have center, spread, and shape, you can then tell a statistical story of truth. You can say with truth and with certainty that indeed the average amount of medals won over the course of all these years was at the Olympics was 5.29. But anyways, that's it, guys. I hope I hope this wasn't too bad. I hope you got a good pump on from this. Not too bad, not too light workout day, guys. Just keep maintaining those mental muscles. Not having to pump them, just maintaining the mental muscles you have, right? Because you guys are looking to be in great shape at this point. We've done a lot with statistics thus far. We've come a long journey. And now there's a few other things in subsequent videos I want to talk about related to statistics at this 6th and 7th grade level. But that's really it, guys. We're nearing the end of our journey on statistics. So, with that said, I hope you found this to be useful. I hope you found this to be informative, and I will catch you guys on the next video. Bye bye.